I want to talk a little bit about polarimetric processing, some of the sort of things you can do, and in particular how it relates to wetlands mapping. We've already seen this slide. I mean, the only thing I really want you to sort of think about is that when you have a single polarization, you acquire the data in the orientation of the antenna. That's fine. If you have three polarizations, you basically got a set of orthogonal axes. And what it really allows you to do is a lot of sort of magic mathematical little tricks sort of thing. So, I mean, most people sort of think of polarimetric data as basically just being color radar, and I guess that's a fairly easy and simple analogy. But the idea being that it's kind of three-dimensional now. Okay, we've got scattering information in three directions, and that's incredibly important because it allows you to do a lot of rotations of the axis and things like that. So again, I alluded to it before. Very simple. You know, for a single channel, you've got a transmitter. It sends out a pulse. You wait for a few milliseconds, and then you start recording the received data, and then the next pixel, which is delineated by the black lines, you've got another pulse sent out, and you receive it. And basically, you're always going to get the same polarization back. So that's a single channel data. You get one channel. Okay, receivers are incredibly cheap compared to transmitters. Okay, so it doesn't take much to add a second receiver to a radar. That's pretty straightforward stuff. And all that happens too in this particular case is you usually have two antennas. One is orthogonal to the other one. So you've got a horizontal antenna and a vertical antenna, for instance. So you transmit, let's say, horizontal, and then you receive two simultaneously on your two antennas. So you've now got two polarizations. And then again, next pixel you do the same transmission and you get your two received. So it's very straightforward. And now you've got two channels, and you can do some magic ratioing and things like that. You can do phase differences, because I talked before about how the data is coherent, and you can look at the differences there. Now you start getting into a fully polarimetric radar. Again, these are very expensive, and the reason they're expensive is because they have two distinct transmitters, and transmitters are very expensive. So you transmit whatever polarization X is, and you receive X and Y, and then you transmit Y, and you receive X and Y back. And when you put it all together, you've got four polarizations. Brian alluded to it a little bit this morning, or early this afternoon, that polarization XY and YX are symmetric. They're kind of the same thing. Okay, so these two are not independent. These ones. So basically, these three, this upper triangle kind of thing, are the three independent ones. This just helps to reduce your noise factor because you can average this kind of data. So really, what are we trying to do here? So, I mean, the issue is that when you look at a target, all other things being equal in terms of reflectivity and all that sort of stuff, the amount of backscattering that comes back is basically proportional to the amount of energy that hits that target. So in this case here, we've got some sort of theoretical object that's out there, and you can see that the return, just the way it's oriented from the H, is probably going to be a little less than the return that we would get from the vertical one, because there's a lot more energy in this direction, or there's a lot more backscattering in this direction than there is in this direction. So no big deal. But now we have the same target, and we start to rotate it a little bit, and you can see that in this particular case, the H is getting bigger, the V is getting a little smaller. So the problem is that we've now got exactly the same kind of target, but we're getting different backscattering responses in both the horizontal and the vertical stuff. And that's kind of a pain in the butt, and so we'd like to sort of fix that kind of problem. So what we can do is, because we've got this horizontal and vertical axis, we can do some magic under the hood. We can start rotating this axis. I mean, you as a user don't see it, but basically we can kind of step through a whole bunch of different orientations until we find some sort of minimum and maximum sort of thing. So in this particular case, I can change that orientation for every single pixel until I find the maximum return. And the idea being that in this particular case, here's your maximum return along the x-axis, your minimum return along the y-axis. Now I'm starting to get the same reflectivity from each target. Okay, so the orientation of the target kind of goes away, and you can infer certain things based on what this rotation angle is. And when I talk about the Touzi filter or a Touzi decomposition, this is one of the parameters that comes out. How much did I have to rotate this pixel to get the maximum return, or the minimum return, which is sort of the same thing. So all we're kind of doing magically under the hood is kind of rotating this. We're not changing your image or anything like this, but we're making measurements as though these two pixels, or these two objects, were kind of aligned like this. So we're going to get the constant amount of backscattering we're going to change the orientation so we maximize the backscattering. And it's really quite a simple process. So here we have a data set taken in Flevoland in the Netherlands. This is a Google image. It just happened to correspond with a data set that I happen to have. And basically, what you can see here, this is a dam, some water flowing through here, and I guess it's flowing. This is a very tall tower. It's probably on the order of, I don't know, 60 meters or so. Got a yacht club there in the blue, and some grass here in the green. So from an optical point of view, that's fine. You can interpret the data quite readily. Now what we do here, and I don't know how many of you are familiar with polarimetric signatures, as I was talking about before, we can step through a whole bunch of different permutations, okay? So like I can change that axis and I can measure the amount of backscattering that comes back from each of those rotated axes. And if you know how to read these things, basically the circular transmits are at the front and back, the vertical transmits are on the left and the right, and the horizontal transmit is in the middle. So if you look at this dam here, back in the previous image, you can see that it has some vertical components, it has some horizontal components, very, very straight, linear sort of breakdowns here, and this is exactly what we're seeing here. We're getting high returns of the vertical here and here, high return from the horizontal. So that basically tells me that it's a nice, sharp structure. It's got lots of sharp corners, and these corners are horizontal. Well, not corners, but these directions are horizontal and vertical. Here we've got this nice tower, okay? It's all vertical, okay? There's no horizontal energy at all. And that shows up quite clearly here. I mean, you've got, again, the verticals are at either end. And you can see I'm getting a lot more return when I'm simulating vertical transmission as opposed to horizontal. As a matter of fact, the horizontal is way down at the bottom there. Okay, so again, I know intuitively right away that this is a structure that is basically has a vertical direction. Return from the yacht club, again, you're getting a lot of horizontal stuff, which is probably coming from the hull of the ship, or the yachts, I should say, and maybe a little bit from the masts. I don't know. I mean, there's some vertical structure there. And if you look at grass, again, this fairly straightforward. You get a fairly constant return, a little bit higher in the horizontal than the vertical, but anyway, based on those kind of shapes, if you know how to interpret those sort of things, you get a very good idea of what kind of structure we have in the target. Again, this is stuff that some of you probably know quite well, some maybe not so much. When you hit a natural target, what ends up happening, you've got this nice horizontal wave or this nice vertical wave, and it gets rotated. It bounces off the trunk and the limbs of the tree, and it bounces off the leaves and stuff like this. And so it comes back slightly rotated from the way you transmitted it. Okay. On the other hand, if you hit a solid wall, it's just like you bang into that wall. It comes back, it's all in phase. So in this particular case, you're going to get some HH return, VV return, and a significant HV component. In this one, most of your return is going to be HH and VV. Okay, so natural targets have a higher HV component on average. Man-made targets have a very low HV component on average if we're talking about solid walls. I won't go into too much of this. All I want you to realize is that every time we hit the surface, HH and VV go in and out of phase. Okay, we talked about it being a coherent target before. So here you hit the surface and HH and VV are in phase here. If I do 2 bounces, it comes down here. Here's the first bounce, so they're still in phase. They come back, they're out of phase. If I have 3 bounces on this kind of structure, in phase, out of phase, and back into phase, okay? So the rule of thumb is if it bounces an odd number of times, the HH and VV are in phase. If it bounces an even number of times, they're out of phase, and it's basic physics. So how do these decompositions work, and what do we do, and what are the sort of things we do? So for instance here, let's say we hit a solid target, okay? And HH is this thing here, so that the magnitude of the return is the length of the arrow, and the phase is the angle that it makes. And HH and VV, if we hit an odd number of times, they're going to be in phase. Okay, so they're going to look kind of the same. I mean, they're both pointing. They both have roughly the same phase. They both have roughly the same magnitude, and I can add them together to make that vector that much longer. Okay, so all the energy, if you add these two of them, is like that. On the other hand, if I have an even number of bounces, it's exactly the same thing. The magnitude's the same, but now the phase is in the opposite direction. Okay? Simple math. If you remember your vector addition, if you subtract this thing, you just change its direction. So again, we got HH minus VV in this case, and it gives us this kind of power. Okay? Why do we care? Well, okay, this is what the radar records. It records basically sort of three axes, whatever the plural axis is. I don't know, HH and VV here, and you can think of HV as being some sort of axis here, and here's your return. And if you sort of think of it on a sphere, it looks something like that. And we can do some magic tricks sort of thing. As we talked about before, if you have HH plus VV and you have HH minus VV, all the man-made targets are going to fall in that plane. Okay, so basically all we've done is we've changed the axis. The vector that returned is exactly the same, and we've changed the axis. So here we talk about HH plus VV. This represents all the odd bounces. This here represents all the even bounces and everything in between. When you talk about dihedrals and cylinders and all those sort of things, they all fall on that axis. Okay, so man-made targets, they're all on that axis using this orientation, and you can see there's no energy on the HV direction. When we do get a return, though, out here, what basically happens is the angle that it makes on this particular plane in the green direction tells us a little bit about the shape of the target. Okay, we know it's a cylinder or a dihedral or a trihedral or whatever it happens to be. So we have this vector here, and we can measure this angle here, and it gives us some kind of idea what the target is. The yellow angle, it's up here, gives us some idea of how natural the target is. Okay, the more unlike a man-made target it is, the bigger this angle becomes. That's just a simple rule of thumb. Okay, so basically, all we're really doing with polarimetry sometimes is changing the axis and coming up with some conclusions. Again, I just wanted to compare single channel versus fully polarimetric. Here in this case, you've got this radar pulse moving along, and you've got these three different pixels at time 1, time 2, time 3. In a single channel, you're going to get some sort of medium return here. You're going to, whatever your transmitter is, it's going to get bounced around a little bit, and you're going to lose some energy, and you'll get a medium value return. Here with water, of course, all the energy is going to hit the water. It's going to bounce off into space, so you're going to get a very low return. And if you hit a nice sort of man-made target, you're going to bounce off the side, and you're going to get a bright return. And that's all you get from a single channel. That's all you know, is kind of how much backscattering comes back. However, when you've got polarimetric data, it bounces around here, and when I look at the phase of the information, it's not anywhere close to what I transmitted, so it's completely unpolarized. It's a volume scatterer. And number two, there's a little bit of energy that comes back, but the little bit that does come back is all in phase, so it's highly polarized, so I know it's something like a smooth surface like water, and I can do some deductions and determine that it's a surface scatterer. And in the third instances, I get a highly polarized return, and I know that it's out of phase, so it's a dihedral kind of scattering effect. So basically the same three targets, but you can draw a lot more conclusions, a lot more, you can infer a lot more stuff. Okay, so general polarizations, the idea being that, yes, we acquire data in these three axes, HH, VV, and HV, but we can rotate them around, and we can do all sorts of things. So when I talk about changes in orientation angle, what I'm talking about is this angle here, where we've simulated a radar that has a rotated transmitter. And when I talk about the ellipticity, it's basically the ratio of the minor axis to the major axis. And again, I won't go into the details about that, but just so you have some background. Just again, some simulated, this is from the CCRS website. You can see a linear, but not horizontal and not vertical. And then, of course, you get all these different ellipses. And these can all be simulated automatically under the hood, and we can step through them all, and we can find out which one gives us the maximum return, which one gives me the minimum return, that sort of thing. So why do you want to do this? Well, here you've got data, HH data, VV data, and you can do all sorts of things. You can identify this area and the land, and you can say, find me the polarization that gives me the maximum contrast. Okay? So here you can see you've got much better contrast between the land and the water. It's the sort of thing that Valentin was just talking about in terms of enhancing the edges and things like that. So again, it's just an interesting mathematical trick. So I can look at both sides of that training area. So I put a training area here, I put a training area there, and I can just look at the contrast. I can look at the power from one, I can look at the power from the other one, and I can just increase the contrast, and all it does is make the edges nice and sharp so you don't get these wind effects. It's a simple process. I won't go into any of this sort of stuff. Last count, our software, I think, can generate about 78 different polarimetric parameters. So this is some very small subset, but you get the idea is that there's all sorts of information you can extract. That's all I really want to say about that one. So here we have some polarimetric data. This happens to be UAV SAR data. If you want to experiment with it, JPL has a site. You can get the data for free. You can get data for volcanoes, marshlands, ship detection, oil spill detection, whatever your interest happens to be. So in this particular case, this happens to be the Louisiana swamp that was affected by that large spill they had last year. That's why I acquired this data set. Just to overlay it up, this is what optical data looks like. So again, the idea being here you've got 3 channels of information, optical data just for comparison. Okay, so what you can do, again, is you can compute polarimetric parameters however you want to do it. So here I have the ratio of the HH to VV channel, and so obviously HH shows bare surface a little better than VV. So in this case here where I've got high HH, you kind of think that's surface bounce. I can do HV over HH, VV over HV, any combination I want to do. If you want to look at them in black and white, that's fine. You can put them all together in color, and you can see that there's a fair amount of information there. Okay, I'm not a wetlands person. I wouldn't know what any of this sort of stuff means, but the idea being that by merging each of these 3 combinations, you can do this, and it doesn't need to be these 3. I mean, like I said, you've got 73 or 74 parameters to choose from. Here I'm looking at phase differences. As you'd expect, where the water is, there's very little phase difference, so that's fairly constant, but some of these other areas have significant amount of phase. And again, you can do HH minus VV, HV minus HH, whatever combination you want to do. You're only limited by your imagination, I guess. And you can put it all together in a color image and you get something like this. And again, I don't have any ground truth for this particular area, but the idea being that there's a lot of subtle information in there, I think, that is of use to different people. Polarimetric discriminators, I can map the maximum polarized part, because every signal that comes back has a polarized part and an unpolarized part, and you can differentiate the two. So there's the maximum polarized part, there's the maximum unpolarized part. Here's the fractional power, which is basically the difference between the two. Like, does it change a lot? So some targets change, depending on how you look at them, their polarization changes a lot. Some targets don't change much at all, so I map that to the blue channel. And again, when I put it all together, I get this sort of nice color composite image. One more example, entropy, which is randomness. Okay, so if you've got a hard target, it will have a very low entropy. If you've got a lot of vegetation that's blowing in the wind, it'll be it'll have a high amount of randomness, which is a high entropy component. And isotropy is basically whether it has a preferred scattering direction. So if you hit water, it has definitely a preferred scattering direction. You hit it like this, the scattering direction is off in that direction. But if you hit something like, I don't know, a tree, for instance, it hits the tree and it scatters in all directions equally. So this is a measure of, so the bright areas are areas that send the radar or the scattering in a preferred direction. The dark areas are scatter in all directions equally. And again, you put it all together, and you get this nice image. And again, I have no idea what it means. So I've kind of combined the two of them, and we'll talk a little bit about the different decompositions. The one that's in use most of the time, I believe, in talking to Brian, is the Freeman-Durden. That seems to be the standard. And basically all we do is we break it up. We have the total power here. We know what that is. We do 2 channels of HV, because the HV and VH are both the same, so that's why the 2 appears there. And based on some ratios and things like that, we end up trying to solve 4 equations with 5 unknowns, and that's okay. And we break up the data into surface power, double bounce power, surface power. I can't read my own. Oh, sorry, and volume scattering, okay? So we basically get 3 returns. So the total power is x, and then we take some fraction of x is double bounce, some of it's surface bounce, and some of it is volume scattering. So again, this is the sort of standard that people have used, and if you want to sort of see what it means visually, the energy that comes from surface scattering, energy that comes from volume scattering, and the energy that comes from double bounce. Very straightforward. So when I break them up into 3 little groups, again, I think Valentine was talking about, so here you've got a lot of reeds. This is the Lac-Saint-Pierre region in Quebec. I don't know if any of you are familiar with that particular area. I'm certainly not, but I can process the data. But there's a lot of reeds apparently here, and there's a big sort of swamp or marsh here, and a bunch of things here. So basically you're getting the double bounce effects from the vegetation along the edge of the water body. Volume scattering, of course. You're getting a lot more of it in these areas. Rough surface, so again, you're getting some energy from the water, and so you're getting the rough surfaces here and here. And again, when you put it all together, you get this nice color composite. I'll enlarge that for you. So I have no idea what any of this stuff means. I'm not a marshland person, but again, the idea is that you've got bag loads of information there, and you can analyze it to your heart's content. The only problem with the Freeman-Durden, that I guess, well, it's not really a problem, but you can, in fact, sometimes get negative values, and some people don't like that, and so they've done some extra research, and they've now come up with what they call a generalized 4-component unitary rotation matrix algorithm or something like that. I just call it generalized 4-component. And it's the same as before. You break it up into surface, double bounce, volume scattering, and now you have this new component, which is helix scattering. And the idea being that, we do some mathematics to eliminate one of those unknowns. So like I said before, you have 4 equations and 5 unknowns, and so there's a bit of ambiguity in that. And what we do is we rotate that axis until one of those parameters becomes 0, and now we have 4 equations, 4 unknowns, and of course you solve for 4 different parameters. And this helix, if you want to think about it a little bit, is kind of if you hit the slope of a hill, you hit the bottom of the hill first and it starts to come back, but then you hit the top of the hill a little later, and so it comes back as a kind of a circular return. Okay, so that's basically what you've broken it up into now. So it's exactly the same as the Freeman-Durden. We still have our double bounce intensity. We have our volume scattering surface intensities, and you can show them all as black and white, and then now you've got this helix intensity. Now I cheated a little bit on this. I had to enhance this image because the helix intensity is quite a bit lower, so it would have been black, but I did boost the image a little bit just to show a little bit of the contrast there. So it looks the same as the other one. A little bit. I could only show the 3 of them, but it's just there for comparison purposes. Anyway, you might, if you're trying to decompose wetland information, this is a decomposition that you might want to consider. Next decomposition is a famous Cloude-Pottier decomposition. Basically breaks things down into entropy, which is a measure of randomness, alpha angle, which indicates the dominant scattering, whether it's surface or a dipole, which is kind of like a reed or a tree, or volume scatterer. And anisotropy, which again is, do you have a preferred direction or not? Does it scatter in all directions equally, or does it scatter in one direction in particular? So here again, we have, the alpha angle, black and white, entropy, which is randomness, and anisotropy. And as you'd expect, the water here shows up much brighter than the land, and that's exactly what you'd expect. It hits the water, it has a very preferred scattering direction, which is often the same direction as the radar's transmitting. From the land, it's not too much preferred, and again, when you put them all together, you come up with this sort of full color decomposition. So again, the swamp or the marsh is here, lots of reeds along the water here and here, urban center there. I have no idea. This is kind of an interesting little area down here. Anyway, basically, this is sort of stuff you can produce. Each of these images takes me about 10 seconds to produce on average. So once you've read in the data, you can just say, this is my input file. I would like this decomposition, and write it to that file. So again, it's very straightforward software. Rita Touzi, who works at the Canada Centre for Remote Sensing, has come up with a very specific decomposition. It breaks everything down into 5 parameters. I alluded to it at the beginning of the talk. Psi is that angle. Remember I was telling you about how much you have to rotate it to maximize the power. Lambda is the strength of the dominant scatterer, alpha s, and phi alpha s are the complex values of the angle that it makes with that axis, that man-made axis that I was telling you about at the beginning when I showed those slides. And tau is that angle that is in the sort of in the latitude direction of the sphere. So basically, you come up with these 5 parameters, and they can uniquely define, well, sorry, not uniquely, but they give you a very good idea of the scattering type of the parameter. And again, you put them all together. So here are the alpha angles, here are the eigenvectors, or eigenvalues, I should say, the helicity angles, and you put them all together, and you come up with a nice decomposition. It looks something like that. And again, each of these are interpreted differently. So you look at them one at a time and you draw your conclusions on what the various target types are. So again, I think the swamp is well delineated here in these yellow and red kind of areas. I think the reds are, like I said, probably reeds or something like some structure that's standing vertically in the water. Okay, so you can take those decompositions and you can do one more step. You can do an unsupervised classification. So you've done the first one and you pass it into the software and you say, you know, this is my first guess, but I'd like you to cluster the data together and put them into different classes and do however many iterations I want to do. So again, very straightforward, your input file, your output file. And what the software does automatically is it classifies them based on what your initial input classes are. So in this particular case, we're breaking them up into high, medium, and low, double bounce, surface bounce, double bounce, yeah, sorry, volume and surface bounce. So based on the colors there, you can classify it. And again, that process takes about 10 seconds to do. Now you compare that to the generalized 4-component, so you can see there's a few differences. This one does not have the helical component. This one does, so some of the energy gets distributed or removed from one classification into another. And here's the kind of interesting thing, I think, is that there's some purple here kind of thing, which would indicate that there's a slight slope to that particular. And yesterday somebody was talking about, I guess if there's water, that these things actually come up a little bit. So again, if you look at these particular areas, or right in here, I think it is. So you look at here, I think it's red, but if you look at it here, it's I guess it's hard to distinguish, but there's a little more purple along this edge here. So I don't know what that means, but maybe that's an effect due to water. Cloude-Pottier decomposition, same thing. You break it up into classes of alpha or entropy, anisotropy, and the alpha angle, and you break it up into these 16 different classes that are predefined. And again, you just get an image like that. And last but not least, you can provide your own supervised classification if you want to, and that's basically, if you know what the area is, you can identify the areas that you find or that you think you know, and what the software will do is it'll automatically find other pixels that look kind of the same as that. So here, like I said, I don't know a bog from a fen, so I just delineated some areas. I said, oh, this looks like water to me. This area here is all these reeds. I identified this as being forest, this kind of area as being agricultural, and this area here being a small urban center. I basically said, go classify. And this is what came out from it. So I wouldn't put too much faith in this because, like I said, I don't know the area at all. But just to show you that, you know, it's a simple thing to do. And last but not least, you can do change detection. You can have an image from year 1 and compare it to year 2. So here you've got total power, and you can do subtraction, you can do ratios, you can do whatever it is you like to do to detect changes. And so the bright areas show you where areas of significant change for this particular parameter. And again, you've got 72 parameters to look at, so you've got lots of things to do. And excuse me, you can just identify where changes have taken place. If you want to map it as the master file in red and the slave file in green and the change in blue, you get this sort of effect where things that are yellow basically are sort of the same. Things that are purple have changed significantly between the reference. Sorry, there's been a significant change because there's lots of blue, and the red it comes from the original reference file. And cyan, of course, represents areas where the slave file had a bigger return value than the reference file. So again, if you look at this sort of thing, you can see some subtle features in here, and you can analyze this to your heart's content. So in summary, I just wanted to say that scattering properties of wetlands can be measured by a fully polarimetric radar. There's lots of things you can do. You've got hundreds of parameters to play with. You can rotate the axis, find maximum power, maximum polarization, minimum polarization, all sorts of stuff. There's lots of useful information in there. Just wanted to say that the data should be calibrated. I keep emphasizing that. If you're going to do monitoring, make sure you use calibrated data, because otherwise it's hard to make comparisons. We tried to cover here today in a half an hour what would normally be a full semester course. So, if you really are interested in this sort of thing, I would recommend that you study up a little bit on polarimetry. It does require a little bit of training to understand how all these decompositions work and how to interpret them and what it means. And last but not least, of course, as a plug for my own company, there is commercial software that's available that will do this sort of stuff for you fairly readily. Of course, there's lots of free software available as well. It's not supported, but basically there are packages. We do read the data from all the satellites that are up there, and all of these decompositions work for all the different satellites.